Now, this is theoretical. In reality, we will use a reduced value, and we call it a design value of K is used. Which means what? Which means instead of using the theoretical value, what do I mean by the theoretical value? That means this PCR, the value you use the theoretical K, then you're going to find the theoretical PCR. However, sometimes we don't use the theoretical value. Sometimes we use the design value. That means you're not gonna use the theoretical value of K to determine the critical load. You're gonna use the design value. So this K here is design. The design value of K, not the theoretical value. What's the difference? The theoretical value can be found from the force equilibrium or bifurcation analysis or the energy approach. But the design value is only empirical. To make sure the final design is conservative, of course, we know that the design value K must be greater or less. Greater or less. Greater, right? It must be greater than the theoretical value. So here I use capital K as the theoretical value of K and the K sub design for the design value. A table that you have seen before from steel design should give you a very good idea about how we used this before, like this. Right? You must remember seeing this table from steel design, perhaps on the steel design manual. And here, the theoretical value, which is in this row, these are determined from force equilibrium. But the recommended design value are usually the ones greater than it. And that explains to what you have. Some of you probably already saw this table or used this table several times in your steel design. Now let's come back to the note. So why this design value? I mean, if you're curious, you may wonder that why we cannot use a theoretical value to predict the critical load. And there are two main reasons. Reason number one is what we call material imperfection. What is material imperfection? For steel structures, perhaps it will be a little bit difficult to imagine, but for concrete, you must appreciate that the heterogeneity of concrete, right? Even you want to use a water to cement ratio to be 0.35, you expect the strength to be very strong, but in reality, according to ASTM and ACI requirements, we have to cast at least three specimens to take the average, then you can determine the compressive strength at the age of 28 days. Why do we have to do it? Because materials or the quality of concrete is not as uniform, as well as it's not homogeneous as one would expect. That's why in the case of buckling, you have to consider that if you happen to have some weak point at the location where the buckling can occur, or the local buckling can occur, then the actual buckling load or the critical load will be much smaller than the theoretical value. So that's what the consideration. Another reason why we have to use the design value rather than the theoretical value is this. It's because there are always residual stress. in real structures. Now, for steel structures and for concrete structures, they all have different sources of residual stress. And I can give you a few quick examples. So what are these? The first one is from what we call material processing. And this is mostly for what? For steel structures. That you can understand. In the manufacturing of steel components or steel members, residual stress can exist. Another major source for the reason for residual stress is during manufacturing or during construction. Due to improper assembly between members. For instance, if you're trying to build a truss member, or a truss member doesn't have residual stress depending on the hinge design. Suppose you're building a frame and you have a vertical frame member, which is like this. And you're supposed to joint the member somewhere exactly to be here to build a portal frame, because there's another column member which was built here. So the original design is just to build the two vertical columns and you join it with a beam member. And suppose the design value of this, and this can be maybe like 30 feet, something like that. However, you notice that one of the columns that you pick on the right is not perfectly straight, right? It actually is somehow tilted. The actual distance here turns out to be 31 feet. So what's going to happen when I actually bring in the 30-foot long column, beam? If I connect this one here, and there's going to be 1 foot distance, right? There's going to be a 1 foot gap, which is right here. When you're forced to connect these two, you're going to introduce residual stress. To the column is going to be an internal moment. To the beam member is going to be tension. So that means once you're forced to join these two, the column will feel a internal moment, which is, it's going to be like this. Force to go here, internal moment will go like this, and the internal tension that you apply to the beam member will be like this. So these tension force and bending moments will become a source of residual stress. So during construction, if the construction is not properly done, there will be residual stress. For these reasons, when we apply the theoretical value of K as a structural engineer, we have to be very careful. and because these will be the sources why our predictions can be as accurate as they should be. Now, the third clarification today, which perhaps is an even more important one because some students asked me this question the first week, and the question is about why the internal moment m sub int has the expression of negative EI times y double prime. Excuse me, I also have similar questions asked in the second week of students. I think that today, 2 examples, we're going to use different expressions of internal moment. And I think it's worth to explain and clarify this concept once for all, so we can move comfortably to more advanced topics. First of all, let's understand 2 different things. The first one is positive definition of moment. And of course, we like to use.
I accidentally hit your car when I was backing out.
Beam.
Yeah.
This will be the easier one.
Oh, it's your car. My car doesn't have anything on it. It's just your car.
Oh, that's fine. It's okay. Just can you just take pictures and just send it to me? I gotta show the mechanics.
All right. I'm gonna ask those who have not muted your microphone, please mute it because we are recording. All right. I don't want to post the videos with your conversation in it. You don't want me to post your conversations in my class videos, right? Okay. I think that's clear now. So, if you have a structure like this, and what is this? What's the shear force? Shear force diagram is going to be like this. Positive shear, negative shear, this is the shear force diagram. And the bending moment diagram, of course, is what? Is a triangle, right? This is a positive moment. This is what we define. Right? You have done this so many times. Now it's a piece of cake to you. So in the deformation of this simply supported beam subjected to the point load at the midspan, the deflection looks like this. Correct? Looks like this. Now if you take a small piece out of it, say we're going to take this piece, just cut it. It looks like this. You have a cell, and your moment, internal moment, acts in this direction. For that, we call this positive moment. This is how we define. Now, one thing that most students, they forgot or they missed that part is, for positive moment, this is just for our mechanics. This, of course, is very easy. But many students did not pay attention to this, the sign of the curvature. And the sign of curvature depends on what? Depends on your coordinate systems. So one thing that you probably did not notice in the past when you learned structural analysis or mechanics. I'm sorry, but I think that my Apple Pen is giving me some troubles today. For some reason, it's losing the signals from time to time.